Good morning, guys, and welcome back to Dynamics course. In this video lecture, we're going to continue chapter 16, which is about rigid body. Now, in this lecture, we're going to talk about and define the instantaneous center of zero velocity. So what is the instantaneous center of zero velocity, and why is it useful to use it in rigid body? If I want to explain the importance of such center or of the instantaneous center of zero velocity, I'm going to go back a little bit to the general plane motion for rigid body. I know that if I have a general plane motion, then in order to know the velocity or the angular velocity of the links or of the beams, I need to apply the equation of relative motion. So I know, for example, that VB is equal to VA plus VB with respect to A. And this means that VB, the velocity at any point B on this rigid body, should be equal to the velocity at A, assuming that this is a general plane motion, which means it includes translation and rotational motion, plus VB with respect to A. VB with respect to A, as we all know, is the velocity of point B with respect to a point A, as if A is the center, and I need to find the velocity of B as with respect to this reference A, and that's why VB with respect to A would be equal to the angular velocity of BA, or of the beam AB. It's the same, but it's cross RB with respect to A. And don't forget that RB with respect to A means I'm pointing towards B from A, which means it's AB. So as if I'm saying that VB is equal to VA plus omega of the beam BA cross, the cross product with RB with respect to A, which is AB. Now, what does this mean? This means that if I need to find the velocity in vector form for any point on the system, I can apply this equation, which is the equation of relative motion. And if I am sure that A is fixed, which means A does not move, or A belongs to the fixed axis, then this means, guys, that I can, for example, remove VA. Now, VA is 0. And then this means that VB is equal to omega BA cross RB with respect to A, which is the same as is the case of pure rotation. So in the case of pure rotation, the velocity was equal to omega cross R, or in other words, it's equal, VB is equal to omega times R, without vector. So in scalar, VB will be equal to omega times R. Now, why I'm talking about these equations in this part of chapter 16, in the part of instantaneous center of zero velocity? Because in fact, guys, if VA is equal to 0, then VB will be equal to the angular velocity times the radius, or times the distance from B to A. Which means if VA is equal to 0, the equations will be much more easier. And this means that if I find the center of rotation, what does this mean? The center of rotation means that the point at which the velocity is equal to 0, because it's at the axis of rotation. If I can find the center of rotation, or the center of zero velocity, like this case, then I'm gonna have an equation of only one term. VB is equal to omega cross R, or VB in scalar form is equal to omega times R, and now R is the distance from B to the center of zero velocity. What differs the instantaneous center of zero velocity from the center of rotation? The center of rotation, like the pin, for example, if I have a beam that is pinned at A, this center of rotation is always the center of rotation, so it's always fixed. However, here, the instantaneous center of zero velocity means that I'm gonna have for each instant a center of zero velocity. If I can find this center at this instant, then I'm gonna make my life much easier. Then I can say that directly that VB or VC or VD will be equal to omega times the distance from this center to my point of concern. Let's take an example. For example, guys, here as you can see, what do I have? I have a horizontal motion for point C, and I have a rotational motion from point B around point A. And this means, guys, that A is fixed, A is pinned, which means VA is equal to 0. I'm sure that A at any instant will be equal to 0. Its velocity is equal to 0. So I'm sure that VB is equal to omega AB cross AB, and VB is perpendicular to AB. What about the beam BC? For the beam BC, guys, I do not have any clear center of rotation like the pin at A. So I need to find it. I need to find this center of rotation, and I'm going to call it the instantaneous center of zero velocity so that I can directly find VB and I can directly find VC. Let's do it. So as I said, guys, here, I know that A is fixed, and this means that VB will be equal to omega times R, and VB will be perpendicular to AB, because A is the center of rotation. So from here, if I know omega AB, the angular velocity of AB, I can find VB directly. Now, what about the beam BC? In fact, for beam BC, I don't have any pin, which means I cannot find out what is the center of rotation. But I have what is called the instantaneous center of zero velocity. How can I find it? In fact, I know that C is always has always a horizontal velocity, so this is VC. So if there is any instantaneous center of zero velocity here, this means that the radius or the line joining this instantaneous center to the point C should be perpendicular to VC, which means this instantaneous center of zero velocity must belong to this line, all right? So it's somewhere here, since I know that VC should be perpendicular to this line, to the line joining the instantaneous center of zero velocity with C. And this is also applied to VB. If there is an instantaneous center of zero velocity for beam BC, then this means that the line that is perpendicular to VB should, then this means that this instantaneous center of zero velocity should belong to the line that is perpendicular to VB. Which means, guys, this is IC. This is the instantaneous center of zero velocity. So I'm gonna repeat, guys. I know that if a point has a zero velocity, then VB will be equal to omega times the distance between this point to point B. And then this means that VB will be perpendicular to the line joining this point of zero velocity to B, all right? Then, if I apply this to the instantaneous center of zero velocity, then VB should be perpendicular to the line joining B to IC, and as well as VB should be equal to this distance times omega BC. And this is also applied to VC. VC is perpendicular to C, IC, and VC will be equal to omega BC times this distance right here. And this, guys, will make, as I said, our life much easier because, in fact, I can directly find the equation of VB without doing any vector equation, any relative relation, because, in fact, VB is now equal to omega BC times the distance between B and this instantaneous center of zero velocity, and VC will also be equal to omega BC times this point C, IC. So this is, in fact, the definition of the instantaneous center of zero velocity, and this is how it's useful to use it. So it's very useful to use it because I can directly find any velocity on the sweep. Even if I put now the midpoint, let's say E, I can say that VE will be equal to omega BC, because E belongs to BC, times the distance between E and IC. And as you can see, guys, IC, it's not necessary that IC belongs to the BBC. I can find IC and it could be outside this beam, but what I have to know is how to find this IC. So whenever I find IC in a correct way, I can directly find the velocity of any point on this beam.